Chapter 15, number 60. A horizontal pipe contains water at a pressure of 120 kilopascals, flowing with a speed of 1.9 meters per second. When the pipe narrows to half its original diameter, what are the speed and pressure of the water? So that's our picture where we have the pipe, and we know that since it gets narrower, we should end up with V2 being greater than V1, which will eventually imply that P2 should be less than P1, but this is expecting that we get actual numbers, so we should walk through and do that. Our first thing to recognize is that if the diameter becomes 1/2 the original diameter, then that implies that the area is 1/4 the original area, because the area is proportional, something like pi r1 squared, and r1 and d1 are moving the same way. All right, and then we have our equation of continuity, and the equation of continuity tells us that the density times the velocity times the area is constant. And we're going to use something that they've told us in the textbook that they explicitly, and we're going to be explicit here too. It's water, which is a liquid, which means that the density does not change, which means I really could have just canceled it out, and I'm left with, when I solve this over, that the velocity is a1 over a2 times v1, which is 1 over a half, right? Or if you want, it's a1 over a half a1. I don't really know the area, but I don't care because it's going to cancel out. And we're going to say that it's twice as fast. So that's 3.8 meters per second. Having used the equation of continuity to get the velocity, we're now going to use Bernoulli's equation to get the pressure. So we're going to know that the pressure plus 1/2 rho 1 v1 square plus rho 1 gy1 equals the pressure in the second case plus 1/2 rho 2 v2 square plus rho 2 gy2. And our key bit here now is to recognize that the densities are the same. So they'll all be rho of water, which we'll get in a second, and that the y's are the same. That y1 and y2 are the same because they don't give us any kind of change in height. So we can basically also just cancel out this entire term because they will be the same. So cleaning this up a little bit, we have P1 plus 1/2 rho v1 square equals P2 plus 1/2 rho v2 square. So I can now just solve this for P2. It will be P1 plus 1/2 rho v1 square minus 1/2 rho v2 square. I'm going to factor that to have only one calculation. v1 square minus v2 square. And now I can throw in some numbers. So 120 kilopascals plus 1/2 times, we'll assume that this is pure water since they don't say anything otherwise. So that's 1,000 kilograms per meter cubed times 1.9 meters per second quantity squared minus 3.8 meters per second quantity squared. 120 kilopascals plus what turns out to be minus 54.14 pascals. And now we have to be really careful because this is basically 120 kilopascals minus 5.42 kilopascal. But we can't have anything better than, to be entirely honest, it's a little fuzzy here as to whether that's 2 sig figs or 3 sig figs. Is that 0 significant? So I'm going to treat it as significant. So we would have 120 minus 5.42, which is 114.58 kilopascals, which should go to, in this case, one digit, or to the ones place. So we get 115 kilopascal. If you did not treat that last one as significant, then it should only go to the tens place, in which case it would be 110 kilopascal. So the difference between the blue and the purple answer is whether or not we consider this to be 1.2 times 10 squared kilopascals or 1.20 times 10 cubed, 10 squared kilopascal. And this is why we don't really like numbers that end in 0 and why we use scientific notation to try and maximize the clarity.